Worksheet 14A, thin gold pressure vessel. The first part, a cylindrical pressure vessel made of A36 steel, has an outer diameter of 6 feet. So again, they give us the diameter and the outer diameter, not the radius. So keep that in mind. The goal thickness T is 2 inches. If the internal pressure, which is P, equal to 1200 psi, what is the factor of safety with respect to yielding? So when we have that, we apply the general design equation, sigma, in this case the yielding, so sigma actual less than sigma allowable. And for the actual here, we want to find out the most critical stress in the cylindrical pressure vessel, which is the hoop stress, because that hoop stress is double of the longitudinal stress, as you remember in our lesson note. So from that, we can get the maximum in here in the cylindrical pressure vessel, which is the hoop stress, sigma 1, less than sigma allowable, which is the sigma yield, right? The yield in this case, the failure of the A36 steel over the factor of safety. The question asks us for the factor of safety, so we can replace all of that with the known input. So hoop stress, and you already have in the note, it equal to P internal pressure times the inner radius divided by the thickness over the yields, sigma yield. So we have that is sigma yield over factor of safety. And from that one, we can be able to find out the factor of safety greater than or less than or equal to in here. So we have that is sigma yield times the thickness over Pi. So plug in, which is number here. We can have sigma yield for the A36, as you recall that is 36 ksi. T, the thickness 2 inches, so same unit, 2 inch, divided by P, P internal pressure 1200 psi, so you have to convert that into ksi, so it will be 1.2 ksi, as you can see there. And then Ri, which is the inner radius. How can we determine the inner radius? It will be apply here the inner radius of the thickness. They have the outer radius, then we have the R outer radius equal to 6 divided by 2 equal to 3 feet. And the inner radius equal to the R radius minus the thickness, and you can see there. So from that we can plug in here. So 3 feet and have to be in. So we have 3 times 12 minus the thickness 2 inches. So the is inches in here. So as you can see from this, the KSI cancel out, inch cancel out. From that we can have the factor of safety here. The maximum factor it can have is, as you can see, 1.8. So that is the answer. The maximum factor of safety for this one is 1.8. Make sense? So that is the first for cylindrical pressure. Now the same question, but they ask what would be the factor of safety if the pressure vessel was spherical instead of cylindrical. Can you predict the factor of safety will be greater or less compared to cylindrical pressure vessel? Why you guess? Let's put out again the sigma actual. And in this case for sphere, you can see the all direction have the same, so which E equal to sigma sphere. And the sigma sphere in this case, as you can see, P R I over 2T. And plug in P already given, this will be 12 PSI. RI, we have 3 times 12 minus 2, so 3 times 12, 36, minus 2 is 24 inch, 34 inches. And you can see, and 2T, 2 inches. So from that, the answer should be PSI. So here it will be 10,200 PSI, and we need to convert that into the KSI, so it will be 10.2 KSI. So that's the actual. So as you can see now, the factor of safety for these scenarios is equal to sigma yield, sigma failure over sigma actual. And in that case, it's sigma yield over sigma actual yielding stress over the actual stress. So it will be 36 KSI divided by 10.2. So it equal to 3.5 factor of safety. So the factor of safety is actually double in spherical pressure vessel instead of cylindrical pressure vessel. And because that with the same thickness, the sphere stress in any direction is only half of the hoop stress. That's why it's safer with the same internal pressure, same thickness for spherical compared to the cylindrical pressure vessel. So that we done for worksheet 14A.